sensory organ. 70% of all sensory receptor cells in your body are in your eye. All right, so think about that. That leaves only 30% of the cells that are involved in sensing every other sense that you have, including other special senses. So your eyeball, in the sense of vision, is a really important sense to us, right? We really heavily rely on our sense of vision to interpret and understand the world around us. So today in lab, we're just going to focus on the anatomy of the eye. In lecture, Dr. Thompson will take you through sort of photoreception, right, and decoding light stimuli. But in order for you to turn light into nerve impulses, you've got to have this really interesting structure. The eyeball is literally a globular ball organ, right? The wall of the eyeball is made up of 3 distinct layers that we refer to as tunics. The outer layer is called the fibrous tunic, and it has 2 major regions. The very front, about 1/5 or so of the eye, is this very crystal clear connective tissue layer called the cornea. And that allows light rays to penetrate into your eye. Because ultimately the sensory receptor cells that are going to decode light stimuli are in the back of the eye. So that first part there, that clear front part of the outer fibrous tunic, is called the cornea. Then the rest of it, the back 5/6 or so, is this opaque white dense connective tissue layer called the sclera. Right? So that's the white part of the eyeball. Moving in, the second or middle layer is called the pigmented tunic. It's called the pigmented tunic because it has color to it, right? The front is a group of muscles that are going to regulate the opening that light can pass through to enter your eye, right? The opening in your eye that light passes through is called your pupil. Right? That's that black spot in the middle of your eye. The colored region around your eye that gives everybody their eye colors, that's called the iris. And it's just like the iris of a camera. It regulates the aperture and the amount of light that can enter your eye. And so it's a group of muscles that can dilate or constrict. So right now in this brightly lit room, all of your pupils are relatively constricted to try to protect your sensory layer from being exposed to too much light. But if we were to turn off all the lights in this room and we were able to darken the room significantly, which we can't really because they put all these big windows, right? It's beautiful for like looking out over the Hudson Valley, but you can't really darken the room very well. But if you were to enter a dark room, your pupil would dilate so it could collect as much light as possible, right? So the iris is the muscle layer that dilates. It's melanin. It's genetically determined, right? So everyone's eye color is determined by the type of melanin you produce and how much you secrete into the iris. So same thing for your hair and your skin tone. So people with dark hair, dark skin, and dark eyes produce a dark colored, lots of a dark colored type of melanin. Now, it'd be nice if it was just a single gene that influenced eye color, but it's not. So it's not as simple as like if you did the big B, your brown eye. So the second part of the muscular layer here in the pigmented tunic is a series of muscles that are more involved in changing the focus or the focal length of the most powerful refractory structure in your eye called your lens. So this kind of silver discoid thing here, which actually is crystal clear usually, that is your lens. So your eye actually has a lens similar to the lenses that are in your microscopes, right? And it's kind of a biconcave piece of connective tissue. It's not ground glass, obviously, right? Unless you have a glass eye. Anybody have a glass eye? Now in your microscopes, in order to change the focal length and the magnification power, you have to switch lenses, right? Because the glass is fixed in terms of its focal distance. Your lens is adjustable. It's very flexible, and attached to your lens is a series of muscles called the ciliary body muscles, and they suspend your lens in the opening here by these things called suspensory ligaments. And when you're focusing on things that are distant from you, far away, right, the refractory power of your lens needs to be less, right, or low, because the light rays are pretty much parallel as they enter your eye. So you only have to bend the light rays just a little bit to get them to focus on your retina. And so your lens actually needs to be stretched thin. And so the ciliary body muscles dilate and they pull the lens and they thin it out and reduce its refractory index. And then you can focus on things that are far away from you. But you can almost instantaneously switch and change your focus to something that's really close to you, right? That ability to change focal length is called accommodation. So you can accommodate really quickly. And in order to do that, though, your ciliary body muscles have to constrict, put slack in those suspensory ligaments, and then your lens naturally plumps up and increases its refractory index so it can really bend those light rays and focus them on your retina for things that are really close to you, right? Now, there is a limit to that, though, right? Your accommodation limit is the distance between your eye and something that you can actually focus on. So if you ever want to find out what that is, you can just take take like a pen. Don't throw it on the ground first, though. And measure how far away the tip of the pen is before it gets blurry, right? So start it out here and then bring it closer and closer and closer until it starts to lose focus. Wow, 13 inches. My accommodation's not so good anymore, right? That's what happens when you get old. That's why you need reading glasses when you get older, right? Because you have to hold things so far away to make them in focus that you can't see like fine print, right? When you're a kid, though, like my kids, when they're reading their books, they're like this. Right? My 9-year-old, she's like, here, Daddy, read this. And she puts it right here in front of my face because that's how far it is. When she can accommodate that distance, right? Just a few inches. Not me. I'm like out at arm's length now, trying to read my newspaper like this, right? So that I need magnifying glasses for that. So those muscles there, the ciliary body muscles, are the ones that help you accommodate. Then the rest of that middle layer there, that red layer on this diagram here, is called the choroid, meaning it has color. That's designed to absorb any light rays that enter your eye that are not absorbed by the sensory layer. So you don't want light rays reflecting around in your eyeball. You want them to either strike a sensory receptor cell and cause a sense of vision, or to be absorbed. So we have acute vision, right? So like right now, I'm looking out at the world, I can actually pinpoint a theoretical spot of light and where it comes from. I know exactly where light rays are coming off of all the objects in my field of view, because basically that theoretical pinpoint of light corresponds to a single sensory receptor cell in my sensory layer. And that cell now knows, okay, that spot of light is that part of my field of vision. This spot of light is that part of my field of vision. So I have basically one sensory receptor cell for every theoretical pinpoint of light that I can expose my sensory layer to. Your visual acuity, right, and the pixel density, if you would, if you want to like make an analogy to a device that you look at on a daily basis, like your cell phone screen or your computer screen, the pixel density on your retina, it far exceeds any pixel density we've ever created for any mechanical screen, right? It is perfect. Our ability to discern two distinct points of light is perfect for the actual ability of our eye to focus light on our retina, right? So it's incredible. In fact, the human eyeball is one of the most highly evolved eyeballs of any other species, right? Now, some species have different aspects, right, that are a little bit more advanced than the human eye, like the ability to see things at greater distances or to collect more light. Like if you're a squid and you live in the dark in the bottom of the ocean, right, your eyeball is more sensitive to light. And if you're an eagle, you can spot a field mouse from 2 miles away. But putting it all together, acute color vision, accommodation, the human eyeball is amazing, right? We have binocular vision, we have depth perception, so it's pretty incredible. So light rays that enter the eye, they either activate a sensory cell or they're absorbed by the choroid. They do not reflect around. When we dissect our cow eyeball, you're going to notice there is a shiny reflective surface in there called the tapetum lucidum. Cows do reflect light out of their eye. Cows are basically nocturnal animals. They have an iris, but it doesn't really constrict all that well. And so they're prey animals, right? They're designed to be able to collect as much light as possible in the dark and be able to respond to predators that are trying to attack them. So they don't actually have acute vision. They just know that there's a predator there if the predator's coming at them, right? They really have more like vision based on motion. So if you stand perfectly still, a cow really can't tell that you're anything different from that. So they do, though, during the day, if they're out during the day, to protect their retina from being damaged by too much light, they reflect light back out. So they don't have acute vision, but we do. So we don't reflect light, we absorb it all. So when you open your cow and you see that really neat kind of bluish, greenish, silvery reflective surface, that's what it is. It's the tapetum lucidum. We don't have that in our eyeball. The final inner layer only covers about the back 3/4 of the eye, depicted by this yellow layer here. That is the sensory tunic, and is also referred to as the retina. Now the retina actually has 3 layers of cells though. The deepest part of the retina, on the bottom or the back side of the retina, that's where the sensory receptor cells are that decode light stimuli. So light has to penetrate through 2 layers of cells before it actually is absorbed by a sensory receptor cell. There's a bipolar cell that regulates signals from the sensory cells to what's called the ganglion cell, which the ganglion cells are on the surface of the retina. Their axons all collect at a spot at the back of your eye called the optic disc, right? And then they exit there and form the optic nerve. Right there, where your optic nerve exits the back of your eye, there are no sensory receptor cells. So if light is being focused on that part of your eyeball, you are not seeing it. Right? So this is also referred to as your blind spot. Now, when you look out at the room, right, each one of your eyes has this blind spot. Do you see 2 black circles? You see 2 black holes in your vision? Why not? You're not seeing light from that spot, right? Light in your field of view is being projected on your entire retina, and you're not seeing the light that's right there. How come you don't have a black spot in your field of view? Make shit up all the time. Your brain is making it up, right? There's 2 things that are going on. The blind spot for my right eye is different than for my left eye. My left eye is seeing what's in my right eye's blind spot, my right eye is seeing what's in my left eye's blind spot, and my mind fills it in. Also, the blind spot is so small that your brain is pretty sure that whatever's right next to your blind spot is the same. And so it just sort of fills in that whatever was, you know what I mean? So what you see is actually just an image that your mind creates for you. It's not exactly how the world is projected on your retina. In fact, the world is projected on your retina upside down and inverted left to right. But that's not how you perceive the world, right? So really, you should not always believe what you see, because your brain is making it up, right? And everybody sees the world a little bit different. It's like the Matrix, right? We are all just a computer program. So no, that's not true. I'm just kidding. But everybody perceives the world slightly different. No 2 people will ever have the same perspective, ever. Right? So just think about that. Well, so everyone perceives color differently. Like what your mind is creating for you with the color of my sweater is slightly different than what Sherry sees or what Grace sees. But we all agree, because we've all learned, that it's some sort of brownish little, speckles of white things, So you've learned that when we show you orange, what you're seeing, we're saying this is orange. To you, it looks slightly different than it looks to me, because we have different organs, right? And different sensory receptor and perception. But we all agree that those wavelengths of light that are coming off that are called orange. How we perceive it is very, very different, right? Now, we're not going to get into color vision and everything like that because we don't have time in lab. But maybe you want to discuss it a little bit with Dr. Thompson. But everybody perceives color slightly differently. But color is determined by wavelength of light, right? And we have sensory receptor cells that are sensitive to any wavelength, right? So we have these things called rods, where they don't discern color. They just say light or no light. And so when you're seeing in dim light conditions, like in the dark at night, you have grayscale vision. You don't have sharp, colorful vision. You just have kind of fuzzy grayscale vision. But in brightly lit rooms, like I see green and red and all kinds of different shades of color, because I have these things called cones. But cones, we have 3 different types of cones, and they're slightly sensitive to different wavelengths of light, right? So we have one set of cones that are slightly more sensitive to the red range. We have cones that are slightly more sensitive to the green range, cones that are slightly more sensitive to the blue rays. But all of our cones perceive light over a spectrum. And your brain literally creates the color for you. So your brain creates a slightly different color than my brain, I'm sure. Right? And some people see more shades of color than others. In particular, women, females, see many more shades of color than males. Yeah, absolutely. How many different shades of green do you see here, right? And some people see 3, some people see 10, right? And women generally see many more slight variations of color than men. We're not going to talk about that because it gets us way off track. Right?
Is that why men are more prone to colorblindness?
No, that's because it's a sex-linked thing. Right? It's an X-linked mutation. So, the retina, though, right, that yellow layer, is not physically attached to the back of the eyeball. It actually is just kept pushed up against the back of the eye in contact with the blood vessels in the choroid via the fluid that's in the eye. So your eye is hollow inside, right? And there's liquid in there. There's 2 major compartments or regions. In front of your lens is called the anterior segment. And there's this liquidy, watery fluid in there called aqueous humor. But the back is the posterior segment. The liquid there is more jello-y. It's called the vitreous because it's more viscous, the vitreous humor. And the vitreous humor keeps your retina plastered and pushed up against the back of your eyeball. Now, the amount of pressure in your eye is critical. You've got to have enough pressure to keep the retina attached. If you don't have enough pressure, your retina can detach and that can cause you to go blind. But if there's too much pressure, you'll compress all the blood vessels in the choroid here and you'll go blind. Not enough pressure, detach your retina. Too much pressure, kills your retina. So you need to just have just the right amount of pressure there. So you constantly make this fluid here, and it has to drain from your eye by these little things called the sclerovenous sinuses, the canals of Schlemm. Now some people develop this increased pressure, intraocular pressure, in a disease called glaucoma. Now how many people go to the eye doctor regularly, right? And they do the glaucoma test and they pump some air in your eye, right? What are they doing? Well, they're looking to see how much flexibility you have in your eye, right? If your eye's got too much pressure, your cornea won't flex very much. But if there's the right amount of pressure, your cornea will flex a little bit. So it's a really fancy machine. Measures pressure in your eyeball. Is that it? Is that all the structures on the eye? Yeah. Okay. So that's your eye. And so vision is a really important sense for us. We use it to orient ourselves in our world. We use it to, understand and perceive our environment, get out of danger, find food, all kinds of stuff, right? The next organ we're going to talk about is your ear. Now your ear has 2 actual really important senses. You're going to have 2 special sensory information coming from your ear. Sound, right? Hearing. Decoding sound energy. What type of energy is sound? It's vibrational, so it's mechanical. So you need a mechanical receptor. And so we'll talk about the organ of chording and how we decode sound in a few minutes. But in order to get the sound waves transmitted to the sensory receptor, which is embedded in the temporal bone in a series of bony chambers with fluid in them, we've got to be able to transmit those sound waves through air, right, and then into that fluid. And so your hearing begins with this really weird looking funnel shaped thing that hangs off the side of your head called the auricle, right, or pinna. So you can call it either one. And that kind of helps to funnel sound waves into this tunnel that runs through your temporal bone, right? Remember the external acoustic meatus? That is where your external auditory or ear canal runs. So the sound waves travel through your outer ear canal here, and then separating your outer ear from your middle ear is this fibrous connective tissue membrane called the tympanic membrane, which you commonly refer to as your eardrum. And literally, it is a drum. And sound waves are banging on the drum like you would hit the head of a drum with a drumstick, right? Basically, that's what sound waves are. They are compression or vibrational waves. So the sound wave vibrations cause the eardrum to vibrate. The vibrations of the eardrum have to be transmitted across your middle ear, which is also filled with air. And to transmit that vibration from your middle ear all the way into your inner ear are these three little bones, the tiniest little bones in your body called the ossicles. And there are three of them. The one that's attached to your eardrum is called the malleus, because it looks like a little mallet. Then the middle one is called the incus, and then the final one is called the stapes, right? Looks like a little stirrup. Now, the inner ear is a series of bony chambers embedded in your temporal bone. There's three major regions or parts to the bony labyrinth in there. The first part, the base of it, is something called the vestibule, and there's an oval window or oval opening, which we can see on this model. This is the inner ear, okay? This oval window is where your stapes is pushing. So there's a membrane between the fluid in your inner ear and the air in your middle ear, and the stapes pushes on that membrane, creating a wave in the fluid that's the same frequency of and amplitude of the waves that are hitting your eardrum, right? And so as that wave of fluid passes through the bony labyrinth, in this part here, which is this kind of coiled up snail shell looking thing, this is actually a tube that kind of rolls up, right? And inside that tube, there is this bony chamber, there's a tube called the cochlear duct, and it's filled with fluid, and we'll get into looking inside the cochlea here in a minute. And that wave of fluid is passing through the cochlea, causing the membrane of that cochlear duct to undulate in exactly the same frequency and amplitude of the sound. Okay? So, the first part, this base, is called the vestibule, and then you have the cochlea, where your hearing receptor is, but then you got all these weird looking canals, right? Semicircular looking canals, and that's what we call them, the semicircular canals. And if you'll notice, each one of these semicircular canals represents one of your body's major planes, right? So, if this is in my ear, I've got one for my coronal plane, I've got one for my sagittal plane, and one for my transverse plane. Those semicircular canals and your vestibule are going to be bringing in information about orientation, proprioception, and motion.
That what we were talking about when we were talking about like vertigo?
Vertigo, yeah. Right? So we'll get into what is the cause of vertigo. What leads to that sort of sick, queasy, dizzy feeling you get, right, when you're spinning around, or you're moving up and down on a ship and you can't find a fixed horizon to orient yourself to, or you get car sick, right? We'll talk about, or if you enter free fall, if you jump off of a high cliff.
What makes you feel like that when you're sleeping? Like you're just falling?
Yes, usually when you're dreaming that you're falling, right, you get a vertigo. I'm not sure.
Because did you ever dream that actually did your alarm clock?
Oh, I do that all the time. I'm dreaming it can't be my alarm clock. I'm still asleep. Yeah. I mean, I don't know enough about dreaming to really pontificate on it. Sorry. But yeah, I think dreaming that you're falling gives you the same sort of mismatch between what you perceive and what's actually happening based on what's going on in your ear. Because when you're sleeping, your ear is telling you what you're doing, right? And your ear sometimes is correct, and sometimes your ear is incorrect. And your body relies on all kinds of different types of proprioceptive information to orient yourself in space, and we'll get into that. Right? So let's talk about first hearing and look at in a little bit more detail about the cochlea. So the cochlea is actually a tube, right? And it just rolled up. So if we unroll it and then cut it in cross section and look inside, right? So if we cut open the cochlea, we would notice that it's actually just a series of chambers. And the cochlea, this is the tube right here, right? Actually, I think I put cochlea somewhere. Oh, she made it.
Yeah, a little out of breath.
So inside the bony labyrinth, right? There are membrane-bound regions, utricle and saccule in the vestibule. There's a membrane-bound tube in the cochlea called the cochlear duct, and there's fluid inside the duct and there's fluid outside the duct, creating distinct chambers. So if we took that cochlea and we cut it, right, in half, and we look into the cochlea, we would notice that in the middle of it is the cochlear duct. And we have the scala vestibuli and the scala tympani, and then the cochlear duct is made up of a connective membrane. On the basal membrane of the cochlear duct, if we blew that up, we would see that there are these really specialized cells called hair cells. And they have these little cilia that stick up into the fluid. But the cilia are not just floating out there in the fluid, they're embedded into this little piece of gelatinous-like membrane called the tectorial membrane, which cantilevers out over top of the basilar membrane. Okay? So they're attached to the hair cells, and then their cilia are embedded in the tectorial membrane. The base of the hair cells are associated with a branch of the cochlear nerve. Now, as sound waves hit your eardrum, right, those sound waves are going to be transmitted across the inner ear by the ossicles. The stapes is going to be pushing on the oval window with the same frequency and amplitude, right, as the sound. As that stapes pushes on the oval window, it creates a wave in the fluid, right? So now we go to an air wave to a fluid wave, right? You ever drop a rock into a pool of water and you notice that the surface of the water begins to ripple? That's what's going to happen to the fluid in your ear. And that ripple, or that wave that passes through this fluid, is going to cause the cochlear duct to also begin to undulate and flex, right? So as that happens, as that membrane is going up and down, what's going to happen to those little cilia? They're going to bend back and forth, back and forth. That bending of those cilia initiates impulses in your cochlear nerve. So there is the receptor. It's a mechanical, it's physically deforming the basilar membrane and bending the cilia of the hair cells that allows you to hear sound. Okay? Now your cochlear duct is a long tube, and if you stretched it out, we would notice that the tube is sensitive to different frequencies of sound in different regions. At the base, near the vestibule, you're most sensitive to high frequency sound, which is higher pitched tones, right? And as you move out towards the tip, now we're more sensitive to lower tones, right, or deeper tone sounds, right, lower frequencies. The volume now has to do with the amplitude, right? So pitch is frequency, and volume is amplitude of the wave. And so we measure sound with a scale called decibels, right? And when you get exposed to really loud sounds, really high decibel sounds, those waves are high amplitude waves, you can actually damage your hearing cells. You can damage the hair cells. And sometimes that's temporary, but sometimes it, repeatedly exposing your cochlea to high amplitude sound, right, or high decibel sound can damage it permanently. Right? So if you work somewhere where there's a lot of loud noise, right, like 100 decibels, you need hearing protection. So if you work like in a warehouse where people are, driving fork trucks around, or you're in a factory where machines are making a lot of noise all the time, they're required to wear hearing protection. Anybody ever work in a job where you had to wear hearing protection? Right? Yeah. They didn't used to do that. That wasn't until maybe like 40 years ago that they came up with this idea that, hey, people are going deaf working in warehouses.
One of the bosses here, one of the police officers, she lost hearing because she just on the platform.
Nobody, right? I mean, I worked in a machine shop since I was 10 years old, and I probably should have wore hearing protection, but we didn't know it. I mean, we knew, but we didn't think that maybe we should protect workers from sound. Right? Anyway, so that's how you hear. It's a mechanical receptor. The other sense we get is from the vestibule and the semicircular canals. That's about position of your body, movement of your body with respect to the earth, right? So gravitational equilibrium and rotational equilibrium. The receptors for that are similar, in fact. They're little mechanical receptors. In your vestibule, you have these two chambers, the saccule and the utricle. And those chambers are lined with an epithelium that have little cilia on the cells, right? Little hair cells. And in those sacs of fluid, though, there are these otolithic membranes, which are like the tectorial membrane, but they're freely floating. And they're a little bit more dense than the fluid because they have some crystals in them. And so when you're standing upright, when your head is upright, they actually touch the little cilia on the hair cells, right? They don't completely crush them, but they're touching them. And that's telling your hair cells that we're right side up, right? And well, it's telling your brain, right? Because now they're sending signals via the branch of the vestibular cochlear nerve into your brain saying you're right side up, you're right side up, you're right side up, right? Now, they're sort of buoyant though, they're a little bit floating in there, but they're still touching. As I start to move forward, those otoliths, because they're floating, they actually lag behind my motion and they float back and it bends the cilia backwards. That lets my brain know that I've begun to move forward. And then they catch up. Then when I stop, they keep going and they bend the cilia forward, and that tells my brain I've stopped. If I tip my head to side, same thing, right? They bend those cilia. So gravitational equilibrium is brought about by these otolithic membranes bending cilia and touching them in your utricle and saccule of the vestibule. However, if I flip my head upside down, I know I'm upside down now for a number of reasons. I voluntarily flip myself upside down. And when I do that, the otoliths lift off the hair cells. And when they're not touching the hair cells, that tells your ear tells your brain you're upside down. Okay? Now, could there ever be a situation where the otoliths lift off the cilia, but I'm still right side up? When you're jumping up and down, right, and you're in free fall. When you enter free fall, right, gravity is holding the otoliths down on the hair cells. But when you fall out from underneath of that, they lift off temporarily. And so that tells your brain, your ear tells your brain, hey, you're upside down. But you know you're not, right? Because you're looking around, no, I'm not, and you know, I voluntarily know I'm not upside down, right? So, you know, you ever been like driving in a car and you go over a bump, and it's like, or in a roller coaster, and when you start to go downhill, right, or jump out of a tree, that entering free fall causes your ear to signal to your brain, hey, you're upside down, but your brain's like, no, I'm not, right? And now you get this mismatch between sensory information. Your ear's telling you something wrong, right? Your ear's telling you went upside down, but all your other proprioceptive information is saying I'm still right side up. But your brain gets a little confused for a second. And so that's what gives you that dizzy feeling, that vertigo, is a mismatch, mostly between vision and vestibular, just going from the vestibule. So if your vestibule is telling you one thing and your eyes are telling you something different, your brain's like, oh, which one's right? Maybe I better just sort of hang on and, you know, can't really orient myself very well for just a few seconds usually. Because usually then gravity takes back over when you hit the ground. And then let's come back down. What if you go out in space though and there's no gravity? That's a problem for a little while. And it takes your brain some time to adjust to zero gravity to be able to orient yourself, right? That's why when astronauts first go out into outer space, they get a little sick. Because the ear is saying, where are we? Where are we? We're upside down. We're not. And your mind's like, no, you know. And then actually, you really can't orient yourself with your vision, and your ear is telling you you're upside down. You're like, I'm not upside down. So you get a little vertigo. Okay?
So what would cause the feeling of vertigo if you're sitting still?
So.
Because that's what, like, my mom just woke up one morning.
Yeah.
And it just started happening, and it was there for a couple of years.
So some people suffer from something called Meniere's syndrome, and then some people have Meniere's disease, which is generally you're getting impulses coming from your vestibule and your semicircular canals and your ear, basically, in the absence of stimuli. And that has to do with an imbalance generally of electrolytes in the fluid. Remember, these cells are electrically active cells. That's what's generating nerve impulses, electrical activity. And so when you have an imbalance of the electrolyte conditions in the endolymph in your ear, that can cause impulses to be generated in your vestibular nerve in the absence of actual stimuli, which gives you the vertigo. You can also have that if you have an ear infection, right? So anybody ever get an ear infection and get vertigo? Right? I had an ear infection, and I didn't have any pain. Like, I didn't know I had an ear infection. I had an ear infection so bad that I got vertigo. Right? I was out with my wife one evening, and suddenly I just literally felt really dizzy. I couldn't walk. I couldn't have balance. I happened to be at a bar, so it looked like I was really drunk, but I was not. I had one sip of a beer, and I'm like, I gotta go home. I'm really sick. And my wife's like, what's the matter? I'm like, I literally have no balance, and it was because I had an ear infection, a massive ear infection. I went to the doctor the next day, and he's like, oh my God, you're not in pain? I'm like, no, I'm not in pain. So anyway, that's what, sometimes you can get vertigo from having an ear infection or Meniere's type syndrome. Remember when you were a kid, you used to spin around in a circle and you get all dizzy, and that was great, right? I hate doing that now, right? As an adult, you're like, I don't tolerate that very well. My kids still do it. They love it, right? They spin around until they get dizzy. I'm like, oh, got it. So why do you get dizzy when you rotate? This is, again, going to be a situation where your vision and your vestibule don't match. So for rotational equilibrium, as we mentioned, you had semicircular canals for each of your body planes, right? At the base of the semicircular canals where it attaches to the vestibule, there's this little expanded region here called the ampulla, right? And in there is a group of hair cells which surrounds the base of the ampulla, and on top of them there's this little gelatinous jello piece of tissue called the cupula. And when you begin to rotate one of your body planes, the fluid in that semicircular canal lags behind your rotation and bends the cupula in one direction. And then as you're rotating it, comes back up. As you stop rotating, the fluid keeps going and bends the cupula in the opposite direction. And so it tells you you've stopped rotating. So just like moving forward and stopping or moving backward and stopping, bending those hair cells in one direction or another tells you when you've begun to rotate in a direction or stopped rotating in that direction, right? So as I begin to rotate to my left, right, my ear says, okay, you started rotating. As long as I'm rotating, I'm actually fine, right? But when I stop, the room's still moving, right? And I'm a little dizzy. Why? Why is the room still moving? It's not, though, right? So, no, the fluid is actually told, and my ear has now told me the correct piece of information, that you've stopped rotating. But I look out at the room, and the room keeps moving. No, the vestibule is correct now. My ear now is correct, unlike gravitational equilibrium when we go into free fall. Now my ear is telling me my mind the right thing, I stopped rotating. But my eyes are telling me that I'm still rotating. And the reason for that is when I go to rotate to the left, my brain sends my eyes to the left briefly and then back to the center. And then while I'm rotating, my eyes continue to dart to the left, to the center, to the left, to the center. So my eyes are going like this, right, while I'm rotating.
So fast, the eyes still go on your side.
Yeah, when you look at their eyes, they're like vibrating, right? And you're like, right? Well, it's because as I go to the left, my brain wants to find out what's there in case I run into something, right? It doesn't matter because your eyes are still moving, and so your eyes are still telling your brain that there's movement. So your eyes continue to move after you stop. So again, you get this mismatch between vision and vestibule, and your brain's like, I think the eyes are usually right? But then your ear's like, no, we're right. And so you get this confusion, right? And so you get this. Now you can stop that. You can train yourself to not get dizzy. And the way you do that is that when you stop spinning, you force yourself to focus on something off in a distance. Like you pick a spot way out in the distance and you force yourself to look at that. And what that does is it stops your eyes from moving.
Is that why skaters spin so fast?
So you ever watch you ever watch figure skating? And they do those rotational things? And they're on ice skates and they don't get dizzy. And then they jump up in the air and they spin around 4 times. I'd fall right over. Nope, they land on ice skates and then they do it again. And then they do that thing where they're like, you know? And you're like, oh yeah, we're gonna stop, right? And then they stop and they're like, oh. It's because when they stop, they look out into the audience and they find some spot to focus their vision on. So their eyes, instead of keep moving, their eye stops. Now their eyes have stopped, their ear says we've stopped, our eyes say we've stopped, and we're not dizzy. So like gymnasts do that, right?
Yeah, I like danced for like 14 years, and every time through the middle, I'd be like spin, like you would like, if you were gonna watch a spin, you would stop, but your head would move around and stop.
Yeah, and it's called spiking, right? You find a point to orient yourself with your vision. You have to make your eyes match your ears. And if you can do that, you don't get dizzy. Now, you can't, that takes some training, right? If you tried that today, you'd be like, I'm trying to focus, but my eyes keep trying to move. So you have to really train yourself to do that. But people do. So that, kids, that is the ear and the eyeball. Equilibrium, hearing, and vision.